Okay, so far we've been talking about double integrals over rectangular regions. Now we're going to do it over general regions because usually we were given what the limits of integration are from x and for y, so it can be from 1 to 2, and then for y it can be from 0 to 3. But they don't necessarily have to always be numbers. They can also be functions. So for example, let's say I had two different functions, okay? So maybe this is my, oops. This is y equals h of x. And let's say you have some other function, y equals g of x. And notice here that you have some sort of area between these two different curves. Okay, so let's say, for example, in three-dimensional space, we try to lay this out. So let's say you have some underlying surface. So you have some surface up in space, in 3D space. So this can be whatever you want. Maybe it's a profit function. It can be, I don't know what. And what you have here is that I'm going to put these, because this is the XY plane. So the XY plane is right below it. Okay, so let's say, for example, we have our two functions right here. Okay, so maybe here are the functions. Okay, g of x and h of x. So notice that they're not rectangular, but I can still form a little cube here. So, well, it's not really going to be a cube, but it's going to be more like I can't draw. Okay, so it's going to look kind of like this. Okay, so you have this type of region here. Okay, so it's not quite a cube, but it kind of looks like it, but you still have volume. So how do we calculate this type of volume? So one way to do it is the double integral over the region R of f of x comma y I'm going to write dA. This can be done using the following. The integral from a to b, the integral from g of x all the way to h of x of f of x comma y dy dx. Now, why is it that way? Okay, so a couple things. I decided to just do dy first, and actually that, for at least for these problems, it doesn't really matter, but at least for the sake of our class, usually a lot of these problems are going to be this way. We're first going to do the y first. Why? Because we know what y equals. Y is between these two different functions. Now, how do I know which function goes on top and the bottom? Well, the function that's always on the top, okay, so this guy's the one that's on the highest, is the one that's going to go on the higher integral, on the higher limit of integration. The one that's right below it is going to be right below it, okay? And then x is just going to be whatever x is going to be, okay? So wherever the region in x is, so whatever this guy is from a to b, that's what x is going to be. So normally you do not want the functions to be on the outer integral, because if they are, you're just going to have x's all at the ends. You always want them to be in the inside. And for the most part, it's always going to kind of look like that. Okay, so let's do two problems where we can really dive into these types of problems. Here's an example. Okay, so what we want to figure out is find the volume under the surface okay, and here is f of x comma y is equal to 12xy, and above the region are shown below. Okay, so usually the region is going to be given to you, at least in this class. So here we have kind of like this petal of a flower. Here is the region R. This lower one is going to be y equals x squared, and this upper graph is going to be y equals square root of x. Here is going to be 1, here is going to be 1, and obviously here is 0. Okay, so you want to figure out what, not the area of this thing is, but if you want to figure out what the volume is. So let's imagine, you don't need to draw this if you don't want to, but just so that you know what you're actually doing. So we have this little petal here on the xy plane, and you have this function up here that kind of looks like this. And imagine that I were to inscribe a petal there, the same thing, you basically are just finding this volume right directly below it. Okay, that's basically what you're doing. You're inscribing this petal and you're just bringing it down and you're finding all of that volume that's in the inside. Okay, so how do you do this? Well, let's first start off with setting up my integral. So the volume is going to be equal to the double integral, okay, of 12xy. Okay, now the way that we wrote it was that we wanted the y to go in the front, okay? So dy is going to be the front. Now, what's going to be in the limits of integration with y? Well, which one is it? Remember, it's always going to be the highest on the top. So the highest is going to be this y equals square root of x, because that graph is directly above it. So that one's going to be up here, square root of x, okay? And the one that's going to be below it is whatever's on the bottom, okay? Which in this case is y equals x squared. So x squared is going to be on the bottom, okay? All right, so that's my dy. Now we need to figure out what my dx is going to be, okay? So dx is going to be just what a to b is. What is going to be the values that are bounding this area. So in this case, in the x direction, it's just going to be from 0 all the way to 1. So from 0 to 1. Okay, so usually this is the hardest part, trying to figure out what goes where. Okay, so now all we're going to do is let's go ahead and just find out what this double integral is going to be. So I'm going to have the integral from 0 to 1, dx is going to be on the outside, and now what I got to do is figure out what this integral in the inside is going to be. All right, so this is going to be with respect to y, so that means 12x is a constant. The antiderivative of y is y squared over 2. And this is going to be between x squared and square root of x. All right. So this is going to be equal to the integral from 0 to 1 of 6xy squared from x squared all the way to square root of x dx. And now we're going to plug that into y, because remember that's the function that we just integrated. Okay, so I'm going to have the integral from 0 to 1 of 6x is just going to be a constant. So I'm just going to plug in the square root of x and the x squared into the y. So I'm going to have square root of x squared minus x squared squared dx. All right, so it's going to be equal to the integral from 0 to 1, 6x. In the inside, I'm just going to have x. And then here you're going to have x to the 4th power dx. Okay, now let me distribute this out. So I'm going to have the integral from 0 to 1 of 6x squared minus 6x to the 5th power dx. All right, and now all we got to do is take the last integral, take the antiderivative of this. So I'm going to have 6x cubed over 3 minus 6x to the 6 over 6 from 0 to 1. So this is going to give me what? 2x cubed minus x to the 6th power from 0 to 1. I'm literally just have to plug in 1. So I'm going to have 2 times 1 cubed minus 1 to the 6th power. That's just going to give me 1. Okay, so the volume that is in this region of this little petal stuff, okay, of this little petal, this entire region is just going to be 1 unit cubed. Okay, so that's basically what we are really solving. Okay, so now what we're going to do, let's do one more problem. Okay. Okay, so here, find the volume under the surface. Okay, and that's going to be f of x comma y is equal to e to the y over the region shown. Okay, and here is the region. So this one is going to be y equals x. This other one is going to be y equals 2x. This is going to be from 0 to 1. This is going to be from 0 to 2. And what we want to do is we want to figure out what this region is going to be. So here's the region R. Okay. All right, so we want to find the volume under the surface. So this guy is in three-dimensional space, and we want to use this region. Okay. All right, so if you want to try it, try it. If not, I'm going to go ahead and do it. So the volume of this guy is going to be the double integral of the function. Now, what's the function in this case? It's going to be e to the y. Okay, notice that we want dy first. Okay, now dy is going to be whatever the functions are that the limits of integration of the y is going to be these functions. So my upper function in this case is this 2x. So I'm going to write 2x on the top. My lower function is going to be this just x. So I'm going to have x on the bottom. Okay, and now I'm going to find my limits of integration for x. Okay, so be very careful because we have two options. We either have from 0 to 1 or we have from 0 to 2. Now remember, this is for x. So for x is going to be from 0 to 1. So this guy is going to be from 0 all the way to 1. Okay. All right, now we are ready to find this integral. Okay, so let's start off with the inside. I'm going to have the integral from 0 to 1. The integral of e to the y is just still going to be e to the y. This is going to be between x all the way to 2x dx. All right, so I'm going to have the integral from 0 to 1. I'm going to plug that in. I'm going to have e to the 2x minus e to the x dx. All right, now let's go ahead and take the antiderivative of this. So the antiderivative of e to the 2x is going to be 1/2 e to the 2x minus the antiderivative of e to the x is just e to the x between 0 and 1. Okay, now let's go ahead and just plug them in. So I'm going to have 1/2 e to the 2 times 1 minus e to the 1. That's my first part. Minus, now we actually have to plug in the 0 because e to the 0 is not 0. So I'm going to plug in the 0. 1/2 e to the 2 times 0 minus e to the 0. Okay, so what is this going to give me? This is going to give me 1/2 e squared minus e minus, let me distribute this out. I'm going to have 1/2 e to the 0. Negative and a negative give me a positive e to the 0. Okay, so this is going to give me 1/2 e squared minus e. E to the 0 is 1, so it's going to be minus 1/2 plus 1. That's just going to give me 1/2 e squared minus e plus 1/2. Okay, all right, and that is my final answer. Okay, so basically this particular answer right here, this guy is what we call my exact answer. If you want to know what the approximation is, you would go ahead and put it in the calculator. But this is the exact answer. This is the answer that we want. So this is the true answer. Okay, so in WebAssign or in anything, this is usually what you would just stop here. Okay, and that's it for integrals over general regions.